Hello, I'm Phil, and this is the pre-lab instructional video for the velocity of electromagnetic signals. And we will be measuring the velocity of light, essentially, which is the electromagnetic signal, in several different media. Basically just in air, and then also in some various types of cable. So, without further ado, let's get on to the first setup, the velocity of light in air. So this is the basic setup for what we'll be doing today for measuring the speed of light in air. We just have a laser that's shooting out light here, and it's going to bounce off of this little piece of glass. Now this piece of glass will reflect part of the beam into one of these little holes in this photodetector here, which is hooked up to an oscilloscope. So what's happening is you have one beam coming and bouncing off and going into this box. Then you have the other part of the beam being transmitted through the glass and hitting the mirror that's going to be located down there and coming back. All right, so once the light beam has gone all the way down there, some distance that we're going to call D in our lab, it'll come back, and now it's aligned such that it will go through this lens and focus and go into the second port on this photodetector here. So essentially what we're measuring is the difference in path that the light is traveling, from going from this little piece of glass here down and back, the distance to D before it hits this box. We're going to assume for simplicity that this distance is traveling between this piece of glass and here, and the reflected beam from here to here is going to be roughly the same, just to keep things simple. So what we're doing is just saying the speed of light is just going to be velocity equals distance over time, where distance is going to be 2 times the distance from here to the mirror, right? Because it's going from here to there and then from there to back. So we can measure that distance with a ruler, or if you're in our lab and have the luxury of just claiming that the floor tiles are 1 foot each, you can use the approximation that that each of these are 1 foot, so you can just count like that. So now that we have an idea of what's going on over here, let's take a look at the oscilloscope to figure out how we're actually going to get our velocity. Alright, so now that we've measured the distance that the light is traveling, we need to look at the amount of time it takes for the light to travel that distance. So what we do is we look at our oscilloscope here, and if everything is set up correctly, there should be 2 waves that are slightly offset on the screen. Now, if you don't get the 2-wave pattern like this, it's preferable that you ask your instructor to fix the setup, because it's really kind of touchy, and even the slightest little bump can set things off, and it just takes a lot of fidgeting to get it back. So when you get this set up like this, then you're good to go. So what we need to do is, if you're using a digital oscilloscope like this guy, you can freeze the screen here by pressing this run stop button, and that will freeze the frame at that moment in time. So now we can do our work on the oscilloscope without worrying about people walking in front of the laser beam and things like that. So first things first is you want to get the time scale on your oscilloscope to be something that's comfortable for you to read. And you can adjust it with this scale button down here, and you can adjust it so that the waves are going to be either bigger or smaller, but as you can see here, you'll need to do that while you can still run with the signal. So if you do need to go back to the case where these things are varying in time on the screen, just hit the run stop button again and it'll start again. Now you can see this is flat because I'm standing in front of the beam, so when I get out of the way it'll pop back into view, and we can adjust now our time scale. So something like this will be too narrow for you to really tell the difference between the top and the bottom, and if you go too far in the other direction, it might become too difficult to see where the actual maximum of those curves will lie. So find something good. I would recommend somewhere between here or here. Your lab manual will have some recommendations about this as well. So once you've found your good setting, you can hit run stop. And now we'll use the nice benefits of this digital oscilloscope to help us on our trek here. So if you are using just the analog oscilloscope, you'll find this time just by using the divisions on here. But if we do have the digital oscilloscope, we can make use of these little bars that you can move back and forth across here. So what you'll do is you just use the knob to position one of these lines on one of the peaks and get it as close to the peak as you can. I mean, there will be a little bit of error here, but just try to get it exactly centered as best you can. Now, when you want to move the other bar, you just hit the select button on this particular model of this oscilloscope, and you can now move the other one freely. So you want to line that bar up with the other peak of the other wave. So when you have that all centered up exactly where you think it should be, you can keep running back and forth and make adjustments as you need to. Now it will tell you the change in time right here on the oscilloscope, so you don't have to do any dirty work. Okay, so this is the amount of time between these two peaks. So for the same peak of light that's coming out of the laser beam that's traveling across that distance 2D, you now have the time that took. So you can just calculate the speed of light from using the equation velocity equals distance over time. Right, now let's move on to the next part of the lab. All right, so for the next part of our lab, we are going to be measuring the speed of light or electromagnetic radiation through various types of cable. In this particular lab, we have RG62 cable, RG58, which you might see the RG8 cable, that's the same one for our lab, and you may or may not have this antenna cable as well. Now the differences between these cables, the antenna cable will have these two wires that are going to be next to each other like this, and the other types of cable, they're just going to be coaxial cable. So that means that there's a single wire coming through the center, and on the outside there's going to be this sheath of wire coiled around. It might be a little bit easier to see on this guy here, where there is this large central wire that's coming through the very center of the cable, and then on the outside is going to be this sheath, which is kind of wrapped around. And that helps for shielding and things. But for the purposes of our lab today, there is also another factor, which will come into play in one of your questions at the end of the lab. So, without further ado, let's go take a look at this. So for this part of the lab, we'll just be using the normal analog oscilloscopes. First what you need to do is you need to set up just an initial signal from your AC power source down here, hook it up to channel 1, and get a 1 megahertz signal. And you're going to want a triangle wave for this one, as opposed to the sine wave or the square wave or anything like that. Put it on a triangle wave. This will give you nice little pointy peaks, so you can do your measurements a lot easier when you're finding the offset between the peaks. Next thing you'll need to do is hook up this power source to have the signal going through one of these cables. So in this example, this is the RG8, which will be the same as RG58 for our purposes. And the way you do that is this. You'll hook the hot line up to either the inside wire or the outside. Doesn't matter which for our purposes, but just make sure that you're consistent. On the other side, if you have the red cable hooked up to the inner wire, that you want the red cable on the back side going to the inner wire. And what you're just going to do is hook that cable directly up to the red input of channel 2. And likewise for the black one. So if you're putting the black cable on the outside of this, the sheath of this side, you want to have the black one going to the outside sheath on that side and going to your oscilloscope. Okay, some things to keep in mind when you're doing this part of the lab is for these cables that are hooking up to the actual cable that you're going to be running your signal through, you want these to be the same length, and you want them to generally be shorter if possible, just so we're not skewing results any more than we need to. One final thing you'll need to really remember to do is to include this resistor. You can put it in a few different places, but right here across the red and black, right on the oscilloscope's channel 2 input is a really good place to put it. The reason we need this is because this thing will help with the impedance mismatch. So if I take this out, well, okay, first here is just channel 1, just the initial signal coming through. Now if I change my oscilloscope to show both of these things and I take out this resistor, you'll notice the waveform gets really distorted and it looks all garbagey. That's from some factors which we won't go into here in this particular lab. So I'm just going to put it back in there, make sure it's nice and snug, so that our waves look more or less triangular-ish. They will be a little bit off because this resistor won't exactly match up the resistance that we need to offset the impedance imbalance, but this will be good enough for our purposes. When you're matching up these resistors to these cables, because of the properties of these cables, the internal resistances and such, you're going to need a different resistor for each cable you use, and the resistor that you need to use is going to be written in the table in your lab manual. So if you have some funny results, just check and make sure you have the correct resistor for the correct cable. So now that we have this, you can see right away that if I switch to channel 1, this is going to be channel 1 on top, channel 2 on the bottom. So if we look at both at the same time, you'll notice that this here's the original signal with peaks occurring here and here and so on down past where we can't see. And now we have this signal going through channel 2, going through all the cable, so that same peak is now going to be offset by a certain amount of time after traveling through this wire of a certain known length, which is written on the cable, or on the spool. So you know the distance because it's written right on there, and you know the time because you can measure this directly from the oscilloscope. Remember, this is going to be the time axis, so you just measure the number of squares from here to here, use your time setting, which is controllable right here on your oscilloscope, and then you have your distance and time to put into your velocity equation. One snag to be very careful of is some people like to use the 2d over t that we use for the speed of light and air. Don't do that here because you're just going through one distance, not two. Okay, now as one final consideration, one of the questions in your lab manual asks you to look at the cables, the differences between the RG62 and the RG58 cables, and talk a little bit about why you think that the speed would be different between these two cables, even though both have the same polyethylene insulation. So what that means is actually go ahead and take a look at the cables face on. Like, look at this guy face on, look at this guy face on. You should notice a little difference between the two, and that should give you a good hint. And with that, that's all there is to this lab. Good luck.